Hello everybody, and welcome to the continuation of example 1. We're still looking at page 86 in the workbook, and our mission is still to determine the number of non-isomorphic abelian groups of a particular order. So in the case of part B here, they'd like us to look at abelian groups of order 16 and to figure out how many of them are there. Okay, how many genuinely different abelian groups of order 16 are there, and then to kind of give a systematic list. Okay, now we saw in the example that we did previously that this has a lot to do with the prime factorization of the order that we're looking at. Okay, so 16 factors as 2 to the 4th, and then what it comes down to is kind of the number of different ways that we can take that factorization and organize it into pieces. Okay, so it's really about the number of partitions, the ways of breaking up the exponent of 4. Okay, so what we're going to do here is to make a list of the so-called partitions of the number 4. Those of you who've taken combinatorics, you may remember the definition of a partition, a way of breaking down a number into pieces. Okay, so one way that we could do that is just to keep the 4 all together. Okay, so we haven't broken it into any parts. We've just got one part that has 4 things in it. But we can also take it and split it into 2 pieces as 1 plus 3. That's another partition of 4. Okay, and one thing that I might add here is 1 plus 3 and 3 plus 1, we're going to consider those to be the same. We don't care about the order, just kind of the number of pieces and then the number of elements in each piece. That's what's important. Okay, so how else could we break down the number 4? Well, we could break it into 2 plus 2. Okay, or we could even take those 2's and break them down smaller. So if you take the first 2 and break it into 2 parts, you would get a partition that looks like 1 plus 1 plus 2. I'm going to give myself a little bit more space here. Hang on. All right, and then anything else we could do? Well, we could break that second 2 down, and then we'd get a partition that looks like 1 plus 1 plus 1 plus 1. Okay, and I think if you think about it a little bit, you can convince yourself that those really are all of the possibilities if we don't care about the order that we're writing down our terms in. Okay, now it turns out that there is a corresponding isomorphism class for each of these partitions. Okay, so we're going to write down an abelian group of order 16 that goes with each of these 5 partitions that we came up with. Okay, so the 4 would correspond to the abelian group that looks like z to the 2 to the 4th. Okay, we're kind of just starting with this factorization and saying we're going to leave the 4 together. We're not going to break it into pieces. And that's really just the group z16. Okay, so there's one abelian group of order 16. Okay, and then what about 1 plus 3? Okay, well that's telling us to take the 2 to the 4th and to break it into 2 pieces, one that looks like 2 to the 1st and one that looks like 2 cubed. Okay, notice if we kind of do the arithmetic, that's really z2 plus z8. Okay, there's another abelian group of order 16. Okay, do you believe that it has order 16? Okay, it has to, doesn't it? Because Z2 has 2 elements, Z8 has 8 elements, and so the product's going to have 2 times 8 equals 16 elements in it. Okay, and continuing down our list, we come to 2 plus 2, so that's corresponding then to z to the 2 squared plus z to the 2 squared. That's really the same group as z4 plus z4. Okay, and then moving down to the third one, that would correspond to z to the 2 to the 1st plus z to the 2 to the 1st again plus z to the 2 squared. That looks like z2 plus z2 plus z4. Okay, and then the last one is just going to look like a bunch of z to the 2's to the 1st, basically. So just Z2 added to itself 4 times, basically, is what we're getting here. Okay, I'm going to go ahead and circle those just so we can get a look at them all together. So there are 5 of these, it appears. Okay, so just before we get too carried away here and forget what we're doing, let's state our answer. There are 5 of them. And I want to just, before we close this video, maybe make a couple of comments about how we really know that each group on this list is its own isomorphism class. In other words, the claim that we're making here is that none of the 2 groups on this list are isomorphic to each other. Okay, so we could start maybe with these 2, Z16 and Z2 plus Z8. How do we know that they're not isomorphic to each other based on the theorem that we stated? Okay, well, that comes down to the number of terms in the product. Remember that? Okay, so Z16, we've only got 1 term in that direct product, and Z2 plus Z8, we've got 2 terms, 2 pieces. And the fact that those 2 numbers are different, the theorem tells us in that situation that the groups can't be isomorphic. Okay, what about the next 2? Okay, how do we know that those 2 are not isomorphic? Okay, well, this time we do have the same number of pieces. So Z2 plus Z8 and Z4 plus Z4, both of those decompositions have 2 terms in them, but what's different about them? Okay, this time it's the orders of the cyclic groups in the decomposition that are different. Okay, so for example, Z2 has only 2 elements, and in the second case, Z4 and Z4, they both have 4 elements, so that discrepancy of having a group that just has 2 elements that doesn't appear down here tells us that those 2 can't be isomorphic. Okay, and I'd encourage you, after this video is over, to maybe go down the list and see if you can convince yourself that each pair really aren't isomorphic. Try to give a reason based on the theorem that we just said.